So let's now talk about votes and Bayesian combination. So the idea of votes is basically that we assign a sample to the class that received the most votes in terms of the class of individual samples, the decision made by individual models. So basic approach is to assign to the most frequent class in the response of the basic classifiers. More generally speaking, we can use a weighted approach where each decisions are weighted by a factor wj. We see here the equations. We are basically summing for each cases with a weight wj. That is, I would say, equal or better than zero, that is positive or zero, for which the sum of weights are equal to 1. That's important to normalize all decisions. So that's, I would say, the general formulation that we can use to represent this notion of weighted votes. It is a parallel combination model. This is linear in the sense that this equation is basically linear, and it is working in parallel in the sense that each hj can do their processing in parallel, and we bring just the output to the combination function. In the case of simple voting, which is the most common case, we just assume that the weights are the same for all models, basically 1 over big L, where big L is the number of members making the ensemble. So this case basically gives the same weight, the same value to each member's decisions. And as such, we can adjust also the weights to represent the confidence in each classifier. If we see in our ensemble, we have some classifiers that are much better performing than others. We can use basically different values of WJ that may be much higher for those high confidence classifiers and much lower for the classifiers that are prone to make more classification errors. And so the voting model looks like this. So we have the input X, which is put in parallel into each individual members here, H1 to HL. And then we have a weight WJ that is multiplied with the output of the HJ corresponding. And then we have this sum that is summing this overall, and that gives us the ensemble decision, which is called H bar. We can show that, in fact, this is equivalent to some extent to the Bayesian combination model, which is more grounded into probabilistic approaches. So the Bayesian combination model tells us that the posterior probability, the probability of assigning to Ci if for an input X, is equal to the sum for all models of the posterior probability of the model. So basically, we look at the posterior for each model times the a priori probability for that model. So this is PM of MJ is not dependent on X. This is something we just said before about the prior over that model. And the posterior is really the decision made for that model over that sample. So according to our modeling made in the previous slides, the prior PM of J is in fact the weight WJ. So this is how we can assimilate that. This is a weight that we just set in advance that correspond more or less to the confidence we have in that model. And we have the decision HJ, which is in fact the posterior here, which is I would say, more informative than a 0-1 decision. It's more about really the probability that the delta X is from the class Ci according to model MJ. So simple voting, majority vote is the case of an a priority called probabilities. So basically all probabilities are the same 1 over big L. And that's it for that modeling. So that modeling is really interesting in terms of just mapping what we do into this Bayesian modeling approach, probabilistic modeling that we saw in the first weeks of the course. So there is a notion of bias and variance in two-class classifiers ensemble. So what we saw before in terms of single models, we can apply it here in terms of ensemble methods. So we assume that each Hj are ID, and we have an expectation in terms of the output that is called Hj, and a variance, a corresponding variance over the individual output that is Hj. And this is the same over all Hj. So from J equal 1 to L, given that we assume things are ID, independent, identically distributed, we can just say it's the same everywhere. And so the expectation for the ensemble here, H bar, is equal to the expectation over the sum. So this is basically the weighted vote approach that we have here, and we assume that the weights are equal, like with basically majority voting. And then we just say that the decision is made as the sum for HHJ divided by big L. Knowing that we are in the IED context, we can say that the expectation here, in the expectation of a sum is the sum of every element of the expectation. So first, this is a constant that we move out here. And then we have the sum from 1 to L over Hj. This is basically the expectation of Hj, but L times. We do L times expectation of Hj because, in fact, we have this sum here, which is summing over the same thing because it is the same over all Hj. So we have L times expectation of Hj. And with this, we just simplify to say that the expectation of the ensemble is the expectation of single models directly. So the bias is not changing. We have the same expectation, so as such, we have the same variance. But in the same expectation, so we have the same bias. It's the bias. But now, if we look at the variance from which we can get, I would say, informative elements, to the variance of the ensemble is in fact also the variance of the sum of 1 over LHJ for all Hj. But then we know that the variance is in fact the squared expectation. If you develop the equation, you will see that it is equivalent to 1 over L squared, which is one thing. And then we have also the L times variance of Hj. This is coming from the fact that Hj are ID, so the variance, individual variance correspond to are the same over all the models. So 1 over L squared times L times var, variance of Hj, give us 1 over L variance of Hj, which is very interesting because it means that the variance decreases as the number of independent voters L increases. So more we have voters in the committee, lower is the variance. It is divided, in fact, by the number of independent voters, assuming they are independent. So with these results, we can say that the ensembles are able to reduce the variance without affecting the bias, because the bias depends on the expectation, which is the stable, and the bias is the expectation, and then the variance, of course, is going down according to the size of the ensemble. So which is great. And as such, if we are able to reduce the variance without affecting the bias, we can assume that the quadratic error in terms of regression, for example, will also be reduced. If we go with the general case, where we don't have we cannot assume the ID hypothesis on the individual models, then the variance of the ensemble is equivalent to 1 over L squared variance of the decision made by each members of the ensemble. Now, this variance is not the same everywhere because we don't assume the ID hypothesis anymore. If we decompose that, we see that it is corresponding to 1 over L squared. Okay, that's coming from that place here. But we have the sum over J of the individual classifier variance plus 2 times the sum of the covariance between each pairs of members in the ensemble. This is interesting because if we are able to see that this covariance is in general negative, we are able to force the ensemble to have some kind of negative correlation, negative covariance, which means that in fact we force the models to make classification errors, mistakes on different samples. We are not just assuming that they are not in general stochastically randomly making mistakes over the set of samples, and they can make the same mistakes in some cases on the same sample and sometimes not. Here we will go further by forcing, if we are able to force the models to make mistakes on different samples, we will induce some negative correlation, and that will be useful to reduce the variance. So we can get an even lower variance than what we've got before. So by reducing the variance, by having some negative correlation, we can reduce significantly the quadratic error. But the trick is that it should not affect the bias. So we should not affect the expected value over the H, which is also difficult to ensure if we have non-IID models and where we are even pushing on getting them negatively correlated. As we push to enforce some negative correlation, the expectation will increase overall. But basic point here is that this is a way to enforce some kind of diversity in the answer of the classifiers of the example. So, and we said that before, and we will say that again many times, diversity is key. We really need to get ensembles that are diverse. So the goal in the training overall is to obtain classifiers that are not making mistakes on the same data samples. And there is, in fact, the counter arguments that it is borderline case without diversity, where we build an ensemble of L models, but they are basically the same model. Maybe they have been trained independently with different starting point, but it's not uncommon to have approaches that will converge to the same model very often for a given data set. So as such, if we build an ensemble with that, there will be no much useful, can I say, need for having an ensemble, because the ensemble will be L copy of the same classifier. Let's just use one copy, that will be enough.